Hi, thank you for joining us. This is the third lecture in a series of 6. And today what I'm going to talk about is modelling continuous clinical outcomes. In fact, I'm going to cover the general linear model, which I guess most people might know as linear regression and ANOVA. I'll explain the subtle differences between those terms in a minute. What I will say before we even start, Bud, is the first 2 lectures in this series, so last week and the week before that, were very much more big picture types of lectures, trying to tell you where biostatistics sits in clinical epidemiology and the clinical research process. Now we're going to get to the nitty-gritty of statistical models, and I'm not going to go too heavy into the mathematics of it, but you will see a couple of symbols here and there now. So this lecture right now, I guess it's a combination of this part here, so just it introduces linear regression, which is sort of like a statistics 101 introduction to linear regression. But then what I want to do is couch the linear regression model in terms of a more general model, which is called the general linear model, where we can bring in categorical predictors as well. In other words, what people call ANOVA. Now, ANOVA is a word, or an acronym, I guess I should say, that I do avoid because it can mean 2 things. It can mean a statistical test where we're trying to see an association between a continuous outcome and a categorical predictor, and that's fine. But it also refers to an quite old-fashioned statistical method that we've sort of moved on from now, and that actually had some limitations associated with it. So the word ANOVA is one I tend to avoid because it's ambiguous. It's ambiguous. The last thing I will say is I want to start, again, I want to relate this to the clinical epidemiology. In other words, how biostatistics fits into clinical research and what it actually means to us. So I want to introduce, and I'm sure everybody's heard of these concepts, but I'm going to talk about them today, and I'm going to talk about them next week as well. And that is the all-important notion of confounding and of effect modification, which is sometimes called interaction. I'm hoping I can get through all of this today. I know I tend to have a habit of making my lectures a little bit long, but just remember they're also reference notes as well, so you can always come back to them and read them. The other thing I will say is this lecture is very similar to a one I actually gave earlier this year, which was meant to be part of the series before we were rudely interrupted by Corona. I'm sort of repeating it. I've sort of changed it a little tiny bit, but I'm repeating it because this is the perfect place for it. Okay, so today I'll sort of just give a very brief overview of linear regression and how it fits into biostatistical modelling. We will cover the basic linear regression model, including the simple linear regression, in other words, the one predictor model. And we'll move on to multivariable models. Then I'll talk about the general linear model. And then these very important concepts here. And these are very important in terms of observational study designs. Okay. So far we have considered, wait a sec, what's happened there? I've just jumped about. Oh, sorry. I must have accidentally hit the table of contents. Wow. Okay. That confused me for a sec. Okay, so I guess I've already mentioned the first one. Today we are going to cover models for continuous outcomes, and I should say continuous normal outcomes. That's actually very, very important. So we're going to cover ANOVA and linear regression, and really we're just going to really show they're the same model, and it's actually a general linear model. Okay, so these 2 things together really make up the general linear model. Next session, I will cover models for binary clinical outcomes, specifically binary logistic regression. Then the session after that, I'm going to talk about time to event endpoints. So survival outcomes or length of hospital stay, those sorts of things. And we're going to cover Cox proportional hazards regression and its relatives, and so other closely related methods. So I will really say collectively, these three types of models and their extensions, I should really make a point, and their extensions really do cover probably about 90% of statistical models and statistical analyses I actually see as a professional bias statistician. So if you can really understand these three sets of models, I really should say, then you are well on your way to being able to analyze a large majority of your own data, okay? Just a very quick note also on continuous variables. People automatically assume when you say a variable is continuous, that it's normally distributed. That is not necessarily the case, even though a large majority are. But there are examples of continuous outcomes that don't have a normal distribution. Probably a relatively common one, and by the way, it's not that common for most clinical scientists, but one that does pop up is that representing something like concentration. So it's bound by 0 for a start. You can't have negative concentrations. So it tends to be a right skewed distribution, a distribution with a tail out to the right. And we'll often use a gamma distribution to model these types of variables, okay? So just note that continuous is not a synonym for normal outcomes, okay? Even though in a large majority of cases, a continuous outcome probably is normal, okay? So if we had concentrations, we should not use the general linear model, ANOVA, linear regression, those types of things, okay? Okay, so what is so very, very important about linear regression is it really sits underneath almost all models that we use in biostatistics, okay? Of course, it underpins the general linear model. They're also known as normal linear models, which is actually probably a better name for them. It's just most people don't call them that. So the general linear model, and really, again, as I've said, it really just marries linear regression and the classical ANOVA model together. Also generalized linear models, which I know it sounds very similar, but is actually a broader family of models, which includes logistic regression, Poisson regression, gamma regression for that matter. And then we have survival type models, so Cox proportional hazards regression. All of these models, including these ones here, linear mixed models, generalized estimating equations, generalized linear models, and I know it sounds like I'm name dropping here, but all of these models have a linear regression underneath them. They're all just extensions to linear regression. So what I'm saying is understanding linear regression. If you don't understand linear regression, you can't really understand any of these extensions to linear regression. So it's a very, very important, it's a fundamental model. That's what we would say. Okay. So to understand linear regression and to understand how most other statistical modeling techniques are really just variants or extensions of linear regressions, we do really need to understand the concept of a model, okay? And I'll just remind you a model when we're talking mathematics here, really actually in all applications, but models are the mathematical representation and usually simplification of the system under study, okay? So really we're just trying to get it right in our head a lot of the times when we think about models. We're trying to simplify, we're trying to reduce something to something we can understand and then, I guess, use to fit to data. Okay, so let's look at our first model. Today we're going to talk about simple linear regression, which means one explanatory variable related to an outcome in a linear way. And here it is here. I will talk about this in a little bit more detail. We can extend this same model and bring in several predictors. Okay, so here we have several X variables or predictors. Okay, I do avoid the word independent variable that a lot of statistics textbooks use because sometimes independent variables are not independent of each other. So it's a misleading term. Okay, so just to clarify, simple linear regression is one explanatory variable related to a response variable or a dependent variable or an outcome variable in a linear way. So the word simple just means one predictor. It doesn't mean easy. It just means one predictor. And linear means that the model must take this form. And what is very, very important about a linear model is it doesn't matter where you are on the x-axis, the y-x relationship is the same. The slope is the same, okay? And that's what the word linear means. It doesn't mean, even if I'm much younger or much older, the relationship between age and systolic blood pressure will be the same. It doesn't change with how old you are, for example. Okay, so the steps that we use traditionally to, I guess, perform a regression analysis, a linear regression analysis, these steps. Now, a lot of the time we don't really think about some of these steps. They're just, we do them, we just don't realize that we're doing them. And in particular, this first one. When we say that we estimate the regression equation, so estimate the model, we're not really doing that. The computer's doing it for us, and we don't even realize the computer's doing it for us. We press a button or we write some code, and magically our software fits the model for us, okay? Much more important to us is this second step, which we want to decide, is our model a good model? Okay, so what do I mean by good? There are a couple of steps in assessing whether a model is good. The first is model significance. And in simple linear regression, that means our single predictor is associated with our single outcome variable. Okay, that's what it really means. Now, just because something is statistically significant, in other words, unlikely due to chance, that's what statistical significance means, doesn't actually necessarily mean it's a good model. However, if it is not statistically significant, it cannot be a good model. So we can rule out a model for being good if it's not statistically significant, but just because it's statistically significant doesn't mean it's necessarily a great model. It just means the relationship is unlikely to be due to chance, okay? So then we would go on to a next step and we would say, well, okay, if our model is quite good, how good is it? We will assess its fit to the data, and we will see, did we choose the right model? And that's what model validity talks about. I'll go into this in a bit more detail in a minute. The last step, and I would say in clinical applications, this is not particularly common. This is not that common unless you're doing a very specific study type, which is a prediction study. Okay, so I would say on some occasions our model is so good that we can actually predict values of our y variable, our outcome variable, using values of our explanatory variable. Okay, but it's only really an objective in predictive studies where we've got a very good fit to our data. And in a lot of cohort studies and observational studies, it's just not that strong of a relationship. Yes, we can say this is a risk factor for our outcome, but that doesn't mean we can go to the next step and actually predict things, say, prognostically. Okay. So let's consider a toy example, and I will go through these three main steps, And again, I'm going to focus on these sub-steps of step 2 because that's, for us, the most important part. Remember, the computer does the first step itself. So let's consider a toy example. We're going to look at systolic blood pressure as an outcome variable in adults, okay? And just note that when I say adults, our clinical population are people from about 17 to 69 years old. Sorry, I shouldn't say the clinical population, I should say the sample we have. The sample we actually have are 17 to 69. Our study population are adults from a particular hospital, and our target population might be Australian adults. Okay, so those are the people we hope our results are valid for, our target population. So our research question is can SBP be explained by age? So is age a driver of systolic blood pressure? Okay, now I should also point out one of the differences between something like linear regression and correlation analysis is that we have to have a very strong scientific basis to believe that our X, age, is a cause of Y, not just that they're related to each other, okay? We need scientific reasoning for this supposition, okay? We can't just do it and see what sticks. We shouldn't just run models and see what's actually identified as a predictor and assume that that is a surrogate for science. It's not a surrogate for science. The science process has to come into this. It has to be logical, and ideally, there needs to be some sort of scientific precedence to suppose that age is a predictor for SBP. So statistics alone can't prove causality. Okay. So just out of interest, and here's a question for you. Do you think this study, and if you were at last week's lecture, this will mean something to you. If you weren't at last week's lecture, I'm sorry. But I'm going to ask, do you think this research question is an exploratory one, a hypothesis testing one, or that this represents a predictive study? I'll just ask the people in the room. Does anyone want to guess? What's that, sorry? It is exploratory, but we are talking about a very specific predictor here. So you could actually say it's hypothesis testing too. In other words, we are answering a question, or we are hypothesizing age explains systolic blood pressure. But you're right in some respects. You could actually argue that it's exploratory. We just want to see. But often exploratory studies will have a lot of predictors. So we're sort of saying, what are the important predictors? Okay? Yeah. So you're not wrong. Probably the one I would say it is, but is the hypothesis test. Okay, because it's a very specific research question. The giveaway is the word, the predictor, is mentioned in the research question. Okay, if I just said, what are the important risk factors? That would be much more exploratory. Okay. Okay, so one step that I would suggest you always make, and it is actually amazing how many people do this, and I should say very quietly, sometimes myself as well, where I just won't eyeball the data. I'm very, very busy and I've got to get through the analysis. But it's a very good idea to eyeball your data first, to actually get a feel for the relationship here. Now, this plot tells me two things, okay? One, we have a weirdo, and we've got to think about whether that person represents a true outlier. In other words, someone who's not a member of our clinical population, so therefore we're actually justified in removing them, or whether they should actually stay. And we can't just remove them just because they're inconvenient. That's sort of, you could argue that's scientifically unethical to do that. But if there's, because, you know, we have got our inclusion and exclusion criteria we've already stated, and this person has slipped by those inclusion and exclusion criteria. So we've got to be very careful that we're justified in removing them, besides the fact that they don't fit our model well. Remember, the model's supposed to fit the data. The data's not supposed to fit the model. Okay, so just be very, very careful about this. I would want to go and look at the person. Is there an error with the data entry? For example, do they have some sort of comorbidity, and we might have missed that. We've just got to be very, very careful. So that's the first thing this plot tells me. The second is that this looks like some sort of positive straight line relationship. In other words, it appears to me, and notice the lukewarm language I'm using, it appears that as people get older, their systolic blood pressure is going up. Okay? So I would expect that our analysis should probably reveal that. So in other words, before I even conduct my analysis, I would be surprised if I do not find a relationship, and I might look back. And that's one of the benefits of eyeballing the data, is there's a reality checking process in there. Because sometimes I might just have typed the wrong thing in my model, and I might accidentally assume there's no relationship. So just eyeballing data is a very, very good idea. Okay, so I'm going to throw some output at you, and it's probably not going to mean anything to you yet, and we're actually going to come back to this output. So I have run this toy data set through R, and here is what it spat out. Okay, so you don't really need to note it yet. We're going to come back to it. Okay, the first thing we want to do, and this is the step one, estimate, that should say line of best fit. I've made a typo there. And remember, the simple linear regression model is, there it is right there. And from our output, there it is, there is our intercept, and there is our slope. Now, what do I mean intercept and slope? I'm going to explain that in a minute. But these are the two numbers that I plug into my model. Okay, just another thing to note here, that I'm using the letter B, the Latin letter B, which is the sample estimate, rather than the Greek letter beta, which represents the true value of that, the value from the population. We don't have the population. We've only got a sample from the population. So we need to estimate what that beta is using B. Okay, so getting those values from the output, I've plugged it into my model. Now, what does that mean? First, I will talk about the process of how it works out B0 and beta1, B0 and B1, or in other words, how does it estimate? Sorry, I'll just turn that off. Sorry about that. Why? Okay, sorry. So how does it get those values? Okay, the process it uses in linear regression is a process where the line of best fit is obtained by minimizing the error sums of squares. Now that sounds technical, but it's a very simple idea. All that the software does is puts a line through the points on the scatter plot such that the distances from that line, when we square them, there they are, squared, are minimized. In other words, how can I fit a line where the sum of those red squares is as small as possible? That's it. And that's where we get the name principle of least squares from, which is what this process is actually called. It really does make a lot of sense. Okay, so what does this B0 and B1 mean, or beta 0 and beta 1? Let's talk about that. So beta 0 is the y-intercept, and B0 is the corresponding sample estimate of the y-intercept. What does it represent? It represents the value of our outcome variable we would expect when our predictor equals 0. So in the context of this problem, we would expect systolic blood pressure to be what value if you are 0 years old, if you are a newborn baby, okay? How much what value would we expect Y to take? In other words, if age is 0, so in other words, this term disappears, we would expect you to have a systolic blood pressure of 98.7, okay? Now, I'll come back to that in a minute. The much more important value, and beta 0 is sort of a silly value in some respects. In a lot of contexts, it doesn't actually make any sense, including this one. The much more important one is beta 1. It's the slope. And again, B1 is the corresponding sample estimate. What this represents is the change in our outcome variable every time we increase X by 1. Okay, so as I get 1 year older, we would expect on average your SBP to change by what value? Going back to the model again, we would expect as I get 1 year older, I'm going to add 0.97 to the systolic blood pressure. Okay, so in other words, every year older I get, my SBP goes up by approximately 1 unit. Okay, sorry, it goes up by about 0.97 to be exact. Okay, now this is much more important, and I'll now explain why. Because we've got two parameters, beta 0 and beta 1, we have two potential hypotheses we could test about those parameters. So basically, we get a p-value from our output. There it is right there, and R tends to give you the exact number, but probably the easiest way is just to go by the stars. That just means p is less than 0.001, okay? So, in other words, we're testing the hypothesis in this case that beta 0 equals 0. Now, what does that mean in words? The systolic blood pressure of a newborn baby, of newborn babies is 0, okay? Against an alternative hypothesis that beta 0 does not equal 0, in words, in terms of this problem, the systolic blood pressure of a newborn baby differs from 0. Now, the very important point is that's just a stupid question to ask for two reasons, okay? Even with newborn babies, would we expect their systolic blood pressure to be 0? Not at all. So it's just not a sensible hypothesis to test. Number two, and probably more importantly here, who's our population in this study? Adults, that's exactly right. So why are we talking about newborn babies? We can't use adults to make statements about newborn babies. So for another reason, this is not a hypothesis we would test at all. Okay? Having said that, you might say, well, why don't we just throw the beta 0 out of the model? That also doesn't make sense because it would force the model, I'll do it for you, to go through 0, and it's not going to fit the data well. So in other words, beta 0 is there for convenience. It's not there to test hypotheses about. In this case, occasionally we do test hypotheses about beta 0, but not today and not in this problem, okay? So the beta 0 there is just for convenience to make our model fit the data better, but we don't want to make any statements or test any hypotheses about it. Let's go to the much more important parameter of beta 1, okay? So our null hypothesis is beta 1 equals 0. Now, what does that mean in words? Age does not linearly explain variation in SBP. Now, I could say it's not linearly associated with it, but that's a weaker statement. That just means correlation. Remember with regression, we can talk about causality. We can use words like explain, okay? Association does not imply explanation. Okay, against an alternative hypothesis of beta 1 not equaling 0, in words, age does linearly explain variation in SBP. In other words, it's important, okay, as opposed to it's irrelevant to systolic blood pressure. Also, I want you to think about that mathematically. And sorry, not being here, you may not see this very well. A slope of 0, in other words, a flat line, means it doesn't matter where you go on the x-axis, the y doesn't change, okay? Whereas slope of non-zero, so a positive upward slope or a downwards negative slope, means as I move along the x-axis, something happens to the y variable. So just mathematically, it actually makes a lot more sense too. Okay, so note that unlike beta 0, beta 1 is central to our research question. In other words, sorry, I'm going to skip all the way back here. Can variation in SBP be explained by variation in age? That's our research question, and beta 1, the hypothesis test about beta 1, answers that question. The hypothesis test about beta 0 is irrelevant to that research question. Okay, so that was the first step. Now that's the 2A. I'm just, sorry, I've got to flick back and forward a little bit, and I hope you can follow me. I just want to show you where we are in this process that I talked about. Did I? Oh, sorry, I went past it. There it is right there. So we have estimated the equation. We've now tested the model significance. We've shown that the single predictor, age, is significantly, can explain systolic blood pressure. Now we're going on to step 2B. So we've explained, yes, it is important, but how good is our model? Now, in linear regression, we use something called R squared. Its real name is the coefficient of determination, and nobody calls it that. Everybody calls it R squared, okay? So what does it do in linear regression? It represents a goodness of model fit, okay? By the way, is it a coincidence that it's R, just like Pearson's correlation coefficient is R? It's not a coincidence. It's literally Pearson's correlation coefficient squared, hence the name R squared. So get the correlation between X and Y, square it, you've got the R squared, okay? What does it actually represent? It represents a measure of the percentage of variation in Y explained by our X. Now that's in simple linear regression, because remember, our whole model in simple linear regression revolves around a single predictor, X, okay? So how much variation in Y, in systolic blood pressure, can I explain by people's age, okay? Now from our output, sorry, I've got to switch back and forward again. There it is right there, okay? There it is right there, 0.4318. What does that mean? It means, from the blood pressure data, that about 43.2% of variation in someone's systolic blood pressure can be explained purely from their age. Now, one thing I do ask people to do, if they haven't come across R squared before, if they've got a hard copy of the notes, is actually write that down, because it's a way of reinforcing how we interpret it in our head. If you go, yeah, I've got it, a lot of the time it will just go in one ear and come out the other as you walk out of the room. Okay, so it is how much of our outcome is explained by our single X variable. So we can show that almost half of people's difference in systolic blood pressure is explained by their age. It's not actually almost half, it's only 43%, but you get my point. Okay, the third sub-step of step 2, okay, I know that's sort of confusing, and I'll just switch back again. Sorry to do this to you. Here it is here. We are now at this step here of assessing, is our model good? We've said, yes, it's statistically significant. Our explanatory power was about 43%, which seems quite good, depending on our expectations, I would say. The third thing is model validity. Now, really, you might even ask yourself, well, why didn't we consider this first? If I chose the wrong model, why am I even asking whether it's good? And that's a valid point. I guess it's the way software spits its information out. There is no reason why I've done this last. I could do this first, okay? So there's three main assumptions associated with linear regression. The first two are very, very easy. Okay, in fact, I'm not going to go into a lot of detail about this today because it actually takes quite a bit of time. So I just want to make sure that I fly through this relatively quickly. The first assumption is that the Y-X relationship is a linear relationship. If it isn't, what am I doing using linear regression? Okay, it's almost like, it's almost common sense. Why would I use a linear model to fit a relationship that is non-linear? I shouldn't do that, okay? So really, I'm just asking, is this model appropriate for this data? The second one is, are the Y's serially independent? Now, this is a question, again, we don't really need to consider empirically. We don't need to use the software to test this or anything. We can usually answer this question purely through study design. What it means is the value of my blood pressure does not depend on the value of your blood pressure, or any observation in the data of blood pressure does not depend on any other observation in the data set of blood pressure. Can anybody think of a case where that's not the case? Repeated measures, okay? My blood pressure today is going to be correlated with my blood pressure tomorrow. So in other words, we cannot use simple linear regression for repeated measures or longitudinal studies. We would be violating that second assumption. Also, if we are talking about multi-center trials, sometimes we will violate that assumption. So for example, if you walk into my classroom, your blood pressure is probably going to go up because you're standing near me and I'm giving you a statistics lecture. Okay, so you could argue I am influencing your blood pressure. Okay? No, we know that it's a relaxing process. That's what I do to relax. I listen to biostats lectures. Okay, the third step, and this is one I would like to go into a lot more detail about, but I just can't. We're going to run out of time otherwise. When we take the part of systolic blood pressure out that we can explain via age, there's something left over. There's a residual or a residue left over, okay? So the part of systolic blood pressure that can be explained by age, we're taking it out. What's left we call the error or the residual. We need to know that there's nothing left in that error that we can still explain. So there is an assumption that the residual, the part of why we can't explain using our model, is normally distributed around zero with a constant variance. Okay, so that ugly little statistical statement there, which really is that in mathematical notation, what I've just said just above it, okay? That the residuals behave like a normal distribution whose mean is zero and has a constant variance. Okay, and I'm not going to go into any more detail about that today. If you have any questions about that particular thing, because usually talking about that takes about 4 or 5 slides, and I'll run out of time. Okay, the step 3. Again, sorry, I know this is annoying to you, going to the steps. The third step, the final step in this process is prediction. And what this is about is if we have a very good model, a very, very good model, we can do this. And I'm saying for most cohort studies, we don't have a model that's that good. But if we do, there's a point I want to make where we can use it and where we can't use it. If the observation we want to predict belongs to our clinical population, it is fine that we predicted. So if we have somebody who is 50 years old, we just simply plug in the number 50 into our model, and we can estimate their systolic blood pressure. So that person's going to have a systolic pressure, sorry, I'm just sort of guessing, like 147 or something like that. We just plug the value in and we can estimate their systolic blood pressure. However, if a person isn't a member of our clinical population, we can't do that. So in other words, if they're 50 years old, they fall in that range of 17 to 69 years old. That was in my sample. So in other words, this is a case of interpolation, okay? Interpolation. However, if they are outside of that age range, if they're a 5-year-old child or an 85-year-old, we cannot use it because we are not making statements about what happens with the age SPP relationship younger than 17 years old and older than 69 years old. We have no idea what goes on in those ranges, okay? So we can only use our model for people between 17 to 69 years old. Anything else is extrapolation, and we cannot use linear regression for extrapolation. Sorry, what was that? If it is externally validated, but that's actually not what I'm talking about, because external validation would be if we used it on a MARTA sample and we went and then tested it on a Royal Brisbane sample and just showed that it also worked on them, that's fine. I guess you could see whether it worked on older people, but you'd sort of really have to refit the model, wouldn't you? Okay, so that's not validation, that's redoing the analysis, okay? Yeah, so it's a little bit of a different issue about, because external validation is about, can I use this model for these other people? But those other people's characteristics are the same as my sample. Do you know what I mean? We wouldn't get a totally different sample, okay? Sometimes people will do it just by looking at the properties where they won't actually formally do it. The other issue I should make, and it's actually a very interesting question, because for prediction purposes, that's exactly when we should use external validation, or all types of validation, not just external. Okay, the other question I should ask is, was this model good enough anyway to use for prediction? No, not even close. Not even close. I mean, there is no magic number to tell you what model is good enough for prediction purposes, but in linear regression, I would expect it to be above a 90% R-squared. You might consider that for prediction. Something that's got an R-squared of 43%, forget about it. It's not even close, okay? So I would never use this model for prediction, regardless of whether they're a 50-year-old or a 5-year-old. It's just not a good enough model. Okay, now extending our model to the multivariable case. Okay, now what do I mean by multivariable in regression? That we have more than one explanatory variable. Okay, now the multivariable linear regression looks exactly the same as the simple linear regression, except that we add a slope for each additional variable. Okay. And that's what it looks like right there. You might go, why are you counting to k-1 rather than k? There's actually a very good reason for it, because we have k parameters. We start counting from 0, not from 1. That's why. It's a bit of an odd thing when people first see it. Okay, so just note that each x variable, each predictor, has a slope associated with it. It has a slope. We're no longer talking about a scatter plot, a 2-dimensional scatter plot. If we've got 2 predictors, it's going to be a 3D plot. If we've got more than 2, we're talking about hyperspace, basically, above 3 dimensions. The other thing I do want to clarify with people, even though most people, I guess, well, are starting to understand it, is we should never use the word multivariate. Multivariate to a statistician means something different. It means multiple outcome variables, multiple y variables. So this is a multivariable model. We still only have one outcome variable, okay? but we've got lots of predictors, so it's a multivariable model. So multivariate regression is where we might have a lot of different Y variables. And it's not that common in clinical studies. I guess you'd say in a lot of machine learning applications, a lot of that's multivariate. But it doesn't come up that often. Factor analysis, I guess, is one area if you're into the psych areas of health. Okay, so I'm going to repeat the steps that we talked about in simple linear regression, and any new addition, due to it being a multivariable linear model, sorry, multivariable? I did say multivariable, didn't I? I'm just going to make sure I don't make my own mistakes. Are now in bold, okay? So in other words, step one, estimated regression equation, it's all the same. It's all the same. It still uses the line of best fit, I should probably say plane of best fit or hyperplane of best fit, but it really still uses the same approach, okay? In the step two, there's a little bit more detail. Now, we're divorcing, I mean, I guess they're not totally separate, but now the notion of model significance is separate from the notion of significance of the individual covariates. In other words, we can have a significant model, but that doesn't mean all of the predictors are significant. It just means at least some of them are significant. Okay, explanatory power. We still have R squared, but we use an adaptation of the original R squared called adjusted R squared. And it adjusts for the fact that we've got multiple predictors. That's why it's called adjusted R squared. Model validity. Again, we've still got linearity, residuals, and independence, like we had before. But often we'll also look at something called multi-collinearity, which I'll talk about in a little bit of detail soon. And this is not an assumption thing, but it's about bang for our buck. And that is the notion of parsimony or parsimony. Some people pronounce it as, I don't know which is correct. I've heard it both ways. And that is really, we might say model efficiency is probably the best way of actually talking about that. And again, if our model is good enough, which it often isn't in most observational clinical studies, we can make predictions. Okay, so really I'm just going to focus on these two concepts because they're the new things here, and then we'll move on. So first I'm going to talk about parsimony. And that is really the principle of explaining the most variation with the least number of variables. Now, this is going to change across different research settings. It really does depend on what our objective is. If we want to consider an exploratory model, then parsimony is not really that important because we just want to identify what predictors are important. We're not trying to come up with a nice little tight package that we can sort of package up and send off to someone else to use, okay? But if we're talking about predictive models, we might want to have as few predictors as possible. Generally speaking, a simple model is most likely to be the most stable model. So it's the most robust to slight changes in the data. It's the one most likely to be externally valid, for example. That I can move from population to population to population and it still works, okay? So this is sort of based on the principle of Occam's razor that the simplest answer is often the best, okay? But just remember, different research applications will consider this more or less important. Okay, so just to really get this point across very simply, let's consider three different models. The first is a simple linear regression and it has an R squared of 50%. The second model has three predictors and it has an adjusted R squared of 97%. And the third model has five predictors and it has an adjusted R squared of 97.5%. So in most applications, which model would you pick out of those three? What's the most efficient? Probably number two. We only have to have three predictors and it gives us 90%. The third model, we add 2 whole additional predictors and it only increases it by 0.5%. Okay? Now, again, it's different for different research settings. But model 2 in most applications would be the one we pick. All right? Okay, so one of the trickiest the issues that does actually arise in multivariable modeling, not just multivariable linear regression, but multivariable modeling, is the notion of multicollinearity. It is a very long word, but really what it means is our x's are correlated. It's as simple as that. I should say linearly correlated to strictly be true. That's all it means, okay? So it's a very fancy word for correlated x's, okay? In other words, our so-called independent variables are not independent of each other, okay? Why is this important? There's a couple of reasons, okay? The first is when we say age has this effect on systolic blood pressure, we want to mean it, okay? We want to actually mean it. Now, here's a very simple textbook example of where we might have a problem, okay? The vocabulary in children, how many words they have in their language, is highly associated with shoe size, how big their shoes are. Do you think shoe size is important? No, it's a surrogate measure for age in children. Okay, so in other words, if we're considering 5-year-olds to 12-year-olds, their shoe size is just another measure for age. Okay, so this is a case where 2 variables are highly correlated with each other and it's going to cause us problems. If I just say shoe size is really important without actually thinking about it, I'm going to look like an idiot, basically. Okay, here we have a very high correlation between age and shoe size. We want to ascribe that which is explained by age purely to age and that which is explained by shoe size, which should be almost nothing, to shoe size, right? We want to be able to partition or separate these sources of variation. Okay, the second issue that comes up with multicollinearity is unstable betas, okay? So in other words, unstable slopes, our estimate. I should say B's, not betas. So what happens is the confidence intervals of our betas gets inflated. It's larger than what it should be. So just to show you what that would look like, the true confidence interval for beta is in black. But what we see when we do the analysis is the red. What type of error is that? Type 1 or type 2? No one can remember this. There's only 2 things. You've got a 50% chance of being right. Okay. Basically, if I saw the red one, I'm going to conclude that I can't say X predicts Y because I can't rule 0 out of my confidence interval. Okay, but if the true one is actually the black line, that's the truth. Okay, so I am committing a type 2 error. I'm failing to identify a proper and true relationship. Okay, now what you want to know is how do you simply decide whether it's going to be a problem for you or not? We have this magical number. There's a couple of different approaches, but there's this magical number called variance inflation factor that we use. And it's really, it tells us how much wider those confidence intervals are than what they should be by a factor of the square root of VIF. So in other words, if we get a VIF of 4, that means our confidence intervals are twice as wide as what they should be. If it was 9, they are 3 times as wide, 16, 4 times as wide, and so on. Okay? In fact, I don't know why people don't use the square root of the VIF, which is really just the standard error expansion. But I don't know, there's probably a reason for it. Okay? What do you want to know? Being practical people who don't really want to necessarily know why, if VIF is less than 5, you're happy. Okay? Now, I've always thought that's very extreme. Some people use 10, by the way. If VIF is less than 10, they are happy. What that really says is if my confidence intervals are only a little bit more than twice as wide, I'm happy. I've always just thought that's a little bit too relaxed. But anyway, I'm not going to comment on it. That is a rule of thumb that people use. If VIF is less than 5, move on with your life. Okay, now I would just like to, the last thing I want to talk about before we finish is how does this all fit into the ANOVA problem? And can we marry these two models, linear regression and the ANOVA model? Okay? So traditionally, and particularly in some fields, if you hear the word linear regression, I certainly do. If I hear linear regression, I think continuous predictors. Okay? If you come from the psychology area, they make no distinction. When a psychologist says linear regression, they mean general linear model. But then when I say linear regression, I mean linear regression. I mean my x's are continuous variables, my outcomes are a normal variable, and that's that. Okay? If I'm talking about categorical predictors, at least traditionally, I would think ANOVA. Okay? But I don't even think that. I think the general linear model. Okay? So we can extend the vanilla linear regression model to also incorporate categorical predictors. Okay? So that might be gender, age, group, those sorts of things, BMI, class, whatever. Okay? Predictors. I meant talking about X variables here. Okay, so linear regression models that are used to perform ANOVA type analyses, okay, or even those that have a categorical predictor somewhere on the right-hand side of the equation, are called general linear models, sometimes called normal linear models, which is a really good name for them because it's very sensible, but not many people call them normal linear models, not in the health field anyway. The reason general linear model is not a very good name is people confuse it for generalized linear models, which sounds almost exactly the same, but means something quite different. They're a bigger family. Okay, they're the extended family, you could think of them like that. And we cover our first generalized linear model next week. Okay, so before we saw a multivariable linear regression model, there it is right there. For convenience, we can write it in a matrix algebra form. Okay, so that means that. All right? Here's the definition of the individual terms, but what am I talking about? I'm talking about that. All right, there's my y variable. Here's each column here represents my x variable. I've got a column also for my beta 0. Okay, and this vector of parameters relates my x to my y, and then I'm left with some residual. Okay? So the reason I'm talking about this form is it's much more convenient form to talk about extensions to linear regression. Okay, so now let's consider our first general linear model, and I'm going to tell you first up, it's wrong. Okay, it's actually wrong, and I want you to spot what's wrong with it. So here we've got SBP, we've got it in terms of a continuous variable age, as before in our simple linear regression, but now I've added 2 additional variables, M, which is a dummy variable for males, and F, which is a dummy variable for females. Dummy variables, also known as indicator variables, are variables that take a value of 1 if the answer is yes, and 0 if the answer is no. So M would be a 1 for me, but a 0 for you. F would be a 0 for me, but a 1 for you. Okay? So if the patient is male, M equals 1 and F equals 0. And if the patient is female, is female, that's supposed to be, God, I've got to fix that up, is female, then F equals 1 and M equals 0. Anything wrong with this? Anything wrong with that model? Yep. That's exactly right. That's exactly right. There's a redundancy there. If I am male, I am not female. And if I am female, I am not male. I don't need both of those variables. If I'm 1 for one, I must be 0 for the other. Okay? In other words, they are perfectly associated with each other. And that model's not going to work. It's over-parameterized. Okay? So really, that's what I explained there. Really, you could say they're collinear, but we don't talk about collinearity when we're talking about categorical variables. Really, I would say that they are perfectly inversely concordant. In other words, if I invert it, they agree 100%. Okay? So what that means is I need one dummy variable for 2 states. And in the case of gender, the 2 states are maleness and femaleness. Okay, so this is a model that would work. By the way, I'm assuming in our data set, we only have 2 genders. So here would be a correct model, okay? In other words, and by the way, it doesn't really matter who is 0 and who is 1, but in this case, I'm saying you are 0 if you are male, and you are 1 if you are female. So that's what the gender dummy variable represents. So no, this looks exactly like a linear regression equation, except there's something weird about it. Gender is not a continuous variable, it's a categorical variable. Okay? Also in this case, note that we are, for no particular reason, using males as the referent. Now that's a very important word, and it's something we come across from this point forward, like when we talk about logistic regression next week. And what that means is the reference group, okay? The point of reference, if you like. Okay, so beta gender is going to tell us the difference in systolic blood pressure from the referent due to being female. So in other words, beta gender represents a mean difference between these 2 groups. Okay, it's not a slope, it's a mean difference. And that's really the only difference when we have categorical variables. Okay, so this may be the first time you've been given the statistical definition of the word referent, and it is an important concept that carries through here. Okay, so I just want to talk about this model, the good model, and the bad model in terms of the matrix algebra I was talking about before. So here we have our 1 for our intercept, we've got our ages, that was our male variable. Sorry, that's our female variable by the looks, and there's our male variable there. And we can see that these disagree perfectly, okay? These 2 variables. So I don't really need this variable. I'm throwing it away. It's redundant. And I'm reforming this X matrix to look like this. There's the 1s for my beta 0. There's the ages. There's the gender dummy variable. Okay. So now I'm going to throw some values in. We're not even going to run software for this. I'm going to throw some values in, and we are going to interpret it. Okay, so first of all, beta 0 equals 100. Beta age, and it's statistically significant. Beta age is 0.333. It's statistically significant. And beta gender equals -25. And it is statistically significant. And what I want you to particularly focus on is number 2 and number 3 and the difference in how I interpret it. Okay, number 2 is a traditional linear regression interpretation. Number 3 is more like an ANOVA interpretation. And if you've got this, if you understand what I'm doing here, you've really got the general linear model worked out. Okay, so beta 0 equals 100. It is the systolic blood pressure, expected systolic blood pressure of someone who is 0 years old and gender male. In other words, if I'm looking at my model, there it is, and the age term disappears because it's 0, the gender term disappears because it's 0, all that I'm left with is the beta 0, okay? So in other words, newborn males have an expected systolic blood pressure of 100. Okay. Beta age is 0.333. Age is continuous, so therefore beta age is a slope. It's a slope. As we age 1 year, on average, our systolic blood pressure should go up by 0.333. P is less than 0.05, so we'd reject HO and conclude age does explain systolic blood pressure. It is a significant predictor, okay? Now here's the different one. Beta gender equals -25, so gender is categorical, and you've got to notice the difference. How we interpret things changes a bit. So what that means is beta gender is a mean difference. When gender is 1, you are female, we'd expect our systolic blood pressure to be lower compared to males by 25 units. That's what the -25 means. In other words, if you've got a value for 1 for gender, then you go down 25 points in your systolic blood pressure. Okay? Since P is less than 0.05, we reject HO and conclude that on average, female SBP differs from males. It's lower. It's 25 units lower, and that is statistically significant. Okay? So in other words, since P is less than 0.05, there is a significant difference between males and females because beta gender was significantly different from zeros. Okay? Males are the reference, so beta gender equals -25 represents the difference from males due to being female. Okay? Now, I just want to show you one application of this, which is very good, and people may not understand that this is a major strength of these multivariable models. We can use these models to work out estimated marginal means. Now that sounds horrible, it probably does, but it actually makes a lot of sense. Now, again, I'm going to start with a simplistic value, which is wrong, okay? But I hope it informs you on how these work. So for example, I could say the mean for males equals 100 because it's 100 plus beta gender 0. In other words, -25 times 0 is 0, so it's 100. For females, it's 75 because it is 100 plus -25 times 1. So 100 minus 25 is 75. The only problem is I've just estimated the mean systolic blood pressure of newborn babies. Remember, our sample is adults. So what I'm going to do is I'm going to take an additional step. Okay? I'm going to plug the average age of people into the model. Okay, now I've calculated it, and I get an average age of 30 years old in our sample. Okay, now remembering that our slope for age was 0.33, I can now work out the estimated marginal means for males and females. Plugging it in, we've got 100 plus 0.333 times 30. A third of a 30 is 10, in other words. So we've got 110 plus 0. Yes. Oh, God, I've done that backwards. 100 plus 10, which is a third of 30, plus 0, because 0 times -25, that gives us 110. Doing the same for females, I'll get a value of 85. So does everyone see where I've gotten those values from? Okay, now I've got a very important question for you. And by the way, that's what our model looks like. And there's the average age right there. Okay, lump. All right, that's very complicated. What I just did then, that's a hassle. Why wouldn't I just calculate the sample mean for males and the sample mean for females? In other words, get all the females, and just work out the mean SVP for them, get all the males, work out the SVP for them. Why wouldn't I just do that? And by the way, I think the point I'm about to make is extremely important, okay? It's a take-home message. Why wouldn't I just use the sample means? I've told you, The answer's up there in small writing. Confounding, okay, confounding. So what happens if my females are older, on average, by 10 years in my sample? The difference between males and females might be due to the age, or it might be due to the gender effect. We don't know. By using estimated marginal means, we are adjusting out age and getting a pure male-female difference, okay? So one word, adjustment. That's why we use model-based means or estimated marginal means. We can adjust out confounders and then get pure effects, okay? It's almost like doing an RCT. We randomize between the group, then any differences between the group is due to the effect of interest. We're doing it artificially. We're doing it statistically, okay? So here's your take-home message. Adjusting estimates is one of the main advantages of using multivariable modeling over the classical bivariate tests, t-tests, chi-square tests. So here's my message to you. When you are doing an observational study, never use t-tests, never use chi-square tests, because they assume all differences between two groups can be explained by a single variable and that everything else is balanced. So age and females and males have exactly the same age distribution, they're exactly the same except for their gender, and that's just not valid. We know that's not valid, okay? And this is just such an important point. Okay, I'm nearly there. Okay, so now I just want to talk briefly about confounding, and I'm going to come back to this next week, the week after. It's also very important to observational studies. So let's say our study is observational, and we note that on average, females are older than males. I've really just made this point. I've made this point of confounding. So by adjustment, we can take out that effect. By using sample means, it's confounded together. Age and gender are confounded, okay? So really, that writing in red is not in red by coincidence. It is so very important. Okay, so really, the last thing I do want to say is that there's three main roles. There's subtle differences for some of these roles, but there's three main roles that a predictor, or I should say a covariate, an X variable, can have on the outcome variable, okay? So if a variable is an X variable, it can be, and it's not of interest to us. So some X variables are in our research question, okay? In a hypothesis testing study. So in that case, we call them the study effect, the X variable of interest. But if they are a covariate, a variable other than our variable of interest, they can play one of three roles, sometimes several of these roles. One, they can just be another independent risk factor, okay? So they are not correlated with my X variables. There's no confounding relationship. There's no effect modification. They are just another important predictor, okay? Another role they can have is they can be a confounder, okay? So something that if we do not adjust for, will actually mess up our interpretation. And the third role they can play is they can be an effect modifier. Okay, now I'm just going to go through quickly and explain the difference between confounding and effect modifier, which at first seems subtle, but they are worlds apart, these ideas. Okay? Okay, so confounding, the definition of a confounder is a third variable. So we have a Y, we have an X. Those variables are of interest to us. A confounder is a third variable that associates with both the Y and the X. So we can consider it a triangle, okay? And we can think of a confounder as an alternative explanation. Now, let me give you a very, very simple example. Okay, I carry out a randomized control trial, randomization fails, and I find all of the sick people are in my control group and all of the healthy people are in my treatment group, and my result is my treatment looks great. Is there an alternative explanation? Yeah, all the sick people were in the control group and all the healthy people were in the treatment group. It might have been the failure of randomization that made my treatment look good, but it's actually not really my treatment. Okay? That would be confounding. A statistical definition of a confounder in the linear regression context is something that changes my slope if I put it in the model as opposed to taking it out of the model. So if the slope of the model changes when I adjust for something, it becomes more important or less important, then that is a confounder. If it has no impact whatsoever, it's just an independent risk factor. Okay? So that is our way of assessing whether something is a confounder. We compare our crude or unadjusted betas with our adjusted ones. If the beta is the same, then this third variable is not a confounder. Okay? It's a very simple empirical way of doing it. So what this really means is to not adjust for confounders will give us an over or underestimated effect size, making us think that our study effect is more or less important than what it really is. And confounding bias, this notion of confounding, is one of the defining features of observational studies. It's a major problem in observational studies, and we need to take measures to actually control it. And that's why everybody loves RCTs, because if randomization works, if blinding works, you don't have to worry about confounding. We can use t-tests. We can use bivariate tests in RCTs. We can't with observational studies. It's much more complicated than that. Okay, the one question I do have to ask you, and I've got to really finish it up really quickly, just to test that you actually understand this. We've got to unlearn a couple of things we've been told in our undergraduate statistics. We all know that statistical significance is important, but is it all important? Now, I've got a question for you, okay? We're interested in finding out if gender represents a risk factor for hypertension in a Thai population. So in other words, gender is our study effect, okay? However, in Thailand, and I lived there for a while, almost everyone who smokes is male, okay? Generally speaking, women do not smoke there. They just don't. Anyone who's a smoker is a male. I'm talking about like 99% of smokers are male there. It's incredible. Okay, so we consider systolic blood pressure as our outcome, gender as our study effect, and we run two models, okay? In the first model, we find that being a male increases your systolic blood pressure by 40 units. By the way, this is not real. I'm just making it up. Okay, so in other words, and it's highly significant. Okay, that's my crude model. Okay, then I also put a smoking variable into a second model. The smoking effect the male effect remains significant. They're 20 units higher, but I noticed that being a smoker increases your systolic blood pressure by 15. However, smoking is not statistically significant, okay? Which is the right model? What's that? Why is that? Yeah, so what happens is the male effect in the first model is not just male, it's male and smoking. In the second model, I try to separate that effect out into a smoking effect and a male effect. So this effect should be a pure male effect, okay? And that's actually not the question I was asking, because in terms of the estimate of the male effect, and I mean due to being a male, not due to being a smoker, this is the correct one. But what I'm after, and this is where people will usually say the first model is the correct model because that is not statistically significant. Wrong, okay? Only when it comes to our statements, our hypotheses of interest, do we need statistical significance, okay? When something is a confounder, we're not guaranteed statistically significant. So in other words, if I use my rules that something has to be statistically significant, a model, all its terms need to be statistically significant, then what I'm going to do is in my paper, I'm going to write the effect of being male is 40 units. I am wrong to tell you that. That's not the effect of being male. That's the effect of being male confounded with being a smoker. It's only when I take the smoking effect out. Okay, in other words, and this is where we sort of should distinguish between sex and gender, I really am sort of more interested in the biological effect of being a male, then the second model is correct. And what point I'm after is people to say, no, you can't use that second model because the smoker effect is not statistically significant. We get too hung up on statistical significance. If we are testing a hypothesis, we need statistical significance. If we're not, we don't, okay? So the gender effect that is most accurate is this one, okay? Because it is not confounded with smoking. Okay, very quickly. So far we've considered the case where we can interpret a risk factor independently of each other. The other thing I wanted to talk about was effect modification. What if gender modifies the effect of age on SBP? Now, this is distinct from confounding, okay? And even at first, they sort of look the same, but they're very different concepts. Sorry, I just went backwards then. Okay, so here we go right here, okay? Here's just a silly little example of males being the blue lines and female being the pink line, and that's the effect of age on systolic blood pressure for these two populations. Would you say that what gender you are makes a difference to the relationship? Looking at those two lines. Yes, okay? We can see for a start that the effect of age on males is more profound. In other words, they go up more every year than females go up. However, they did start at a lower level, okay? So what we would say there is that gender modifies the effect of age on systolic blood pressure. And it also means I can't say something like age impacts blood pressure. Why not? Because it's not true. Age impacts systolic blood pressure for males, but it doesn't seem to have too much of an effect on females. Okay? So what that really means is when we have effect modification and interaction, we can't talk about the main effects just by themselves. We need to talk about them together, okay? So from that slide, it appears that the nature of the SBP-age relationship is modified or interacts with the gender effect, and it is an effect modifier. And what I do, and I'm not actually going to go through this because I've just run out of time, is I sort of just go on to show here how that does affect it, which is a real pity because this is actually a really good take-home point here, that what we can do is fit a model for each and see if there's a statistical difference between these two models. If there's not, there's no effect modification. If there is, we can't just talk about a single universal model. And really that's the point I wanted to make. Should I talk about it or should I just end it here? How are we feeling? A bit, We'll take a vote. Do you want me to talk about it? It'll take about 5 minutes. Okay. Are you giving me 5 minutes? And I've got to finish by then. No, that's okay. I'm just stirring now. Okay, so effect modification is often called an interaction and it represents a multiplicative effect. Now, I'm talking stats now, okay? The main point I want to make, but effects by themselves, we tend to call main effects. When we talk about them together, we call them an interaction effect. And as you can see right there, it's multiplicative. What is very important, and people seem to forget this, is if there is an interaction effect, we cannot talk about A by itself or B by itself. We can't talk about the effect of age by itself, or we can't talk about the effect of gender by itself. And that makes a lot of sense if you think about it, but people do forget that. So now what I'm going to do is I'm going to talk about our same general linear model term. So that's what we saw before. There's beta age, beta gender, but here is our interaction effect. There it is right there. So if we use males as the referent, and I'm not even plugging numbers in here, if we use males as the referent and plugging the values of the dummy variable, then this whole model just simplifies to that. Okay, now it makes a lot more sense, the word referent, because males provide us the referent regression equation, which was the blue regression equation back here. Okay, and everything else we are comparing to that. So the females, that's all a little bit messier. We plug the 1 in here, okay, and then by just doing a little bit of rearrangement, okay, we get this model. So we get the difference in intercept due to being female and the difference in slope due to being female. And this is the important one. We want to know, is there a significant difference in the slope due to being female? Now, forgetting about this mathematical form of it, let's talk about this graph. Do you think there was a big difference between the slope for females and males here? Just looking at it. So males are the blue and females are the pink. And by the way, I don't mean statistically significant, I mean important. In your mind, do you think it matters whether you're a female or a male? Is there a preference? Would you rather be female than male? I would, and I'm not saying that universally, I'm just saying in this case with systolic blood pressure, I think I'd want to be a female here. Life seems a bit less risky for them, okay? Now, because I would prefer that, that means it's probably significant, at least in my mind. I don't mean statistically significant, I mean clinically significant, okay? Now, just looking at that, is the slope lower or higher for females? Lower, it's flatter, isn't it? So, if that's the case, and I just want to check that you understand this relationship, do you think, because that's the difference in slope due to being a female, that's the reference slope right there, do you think that would be a negative number or a positive number? Yeah, you're right, negative, because it's reducing the slope, sorry, I'll do it for you, it's reducing the slope of males to females like that. So in other words, this beta age times gender is negative because it's a smaller slope. It's a slope closer to 0, okay? And if that is statistically significant, then that represents significant effect modification. So here's our model for males. There's the difference in intercept due to being a female. There's the difference in slope due to being female. So again, I just want to check this with you. So the difference in intercept, I want you to tell me whether that's positive or negative, and that's positive or negative. So this one, okay, is the intercept higher or lower for females? Is the intercept higher or lower for females? It's higher, isn't it? There it is. So that is the value of beta gender right there. That is how much higher it is. And we've already discussed that that is negative because it reduces the slope. Okay. So the one thing I didn't cover today was the notion of model selection. And by the way, nor will I get a chance in this series of lectures to actually discuss it. It might be one we actually add next time. The reason I don't really want to talk about model selection is the strategy we use changes a lot from exploratory modeling to hypothesis testing to prediction. It's actually quite a different process. Okay, what I did do today is, because we only had a limited number of covariates, is I just forced them all into the model. But you should be aware of other model selection strategies. Stepwise, which is a terrible method for model selection in most cases, but the most commonly used one, because it's a default in SPSS probably. There's also one called best subset. This is one of my favorites, purposeful selection of covariates. Okay, so the first thing I'd say is these linear models when you first look a bit horrible, but they're really not. It's very simple, and the important thing is that you understand why, not how. Okay, you don't really need to understand exactly how they work, but more how to interpret it. So just note, remember that biostatistics is not a content-based area, it's a process-based area. So a lot of the time it doesn't make sense to you when you first cover it, but it slowly creeps in there, unlike content area where you sort of go, oh yeah, I get it. Okay, so just understand you're not alone, you can always talk to us about these sorts of issues. Any questions?
Do we always need to build an explanatory power before building a
Okay, so I'll just rephrase the question and we'll keep the second one. So the question was, do we have to always build an exploratory model before we get to predictive models? What I would say about that is very rarely do we as an individual do both. Okay, so usually exploratory models have, I'm working on predictive models, someone's done exploratory models ages back, it's in the literature. It's also mixed in amongst hypothesis testing models. So if I'm going to build a predictive model, I'm going to measure covariates that I have a very strong belief should be measured. Okay, so let me give you a perfect example. If we're doing biomarker analysis, so something like genomics or any of those high throughput areas, they're very much exploratory, aren't they? Okay, because we might get 10,000 genes if we're talking about genomics, and we want a much smaller set of 10 or 15 genes that we might be able to use for diagnostic or prognostic purposes, okay? Or something like that, something where we can predict for individuals. Now, technically speaking, if we've got no idea which genes are important, we should not be building predictive models in that process. Okay, by the way, people do. What we should really do is use something like, I don't know, some of the high throughput technologies to identify a core set of likely predictors. Then we should do another study using more reliable laboratory techniques to measure those biomarkers and then use it for predictive purposes. So in other words, it's a different study, often not even done by the same teams, but even when it's done by the same team, you wouldn't just go and collect a bunch of microarray stuff on 500 people and then expect to come out with a reliable predictive model. And this actually relates to what you were talking about before about external validation. The crisis that we see in a lot of biomedical stuff, where people come up with these beautiful results, they publish in Nature, and no one can replicate their work because the models just don't work. That's that happening right there, okay? And what's going to happen is journals like Nature and the big journals, they're going to wise up to this eventually, and they're going to expect an external validation process as part. If you want to make statements about predictability, you need to do external validation. And they will wise up to it. I don't know how long it'll take them, but that's the case. So what I would say, and I assume you're asking in terms of your own study, and I mean, I know in your area you can sort of get away with it a little bit more, but that's more forecasting. You're going to sort of be doing forecasting rather than predicting for individuals. So your study is ecological. It's a little bit out by itself. It's not the same as saying for this patient. And you got to remember, we're taking a very big risk to diagnose or fail to diagnose or say someone's negative when our models have not been validated well. You know, that's really mess up someone's life. You can kill them by doing that. So it should be a very rigorous process, okay? And exploring through to prediction is very rarely done in a single study, and nor should it be. I'm sure there are exceptions to the rule somewhere, but in a large majority, it certainly shouldn't be, okay? And your second question? Mm-hmm. Now that's going to do something different to your model, okay? So you think about it, your referent group is beta 0, okay? If you make 1 for males, that's going to do something above that referent, and 2, so no, it doesn't work. It must be 0, 1. One thing I didn't talk about is what happens when we've got 3 groups. We need to set 1 group to 0, and then we get 2 dummy variables, okay? So in other words, for G groups, we mean we need G minus 1 dummy variables, and they're all going to be 0 and 1, okay? So no, it doesn't work if you do that. So one thing I'll always advise people who are seeing me is if you're going to code your variables, always use 0, 1, or a lot of the time I'll just modify it. Like Stata and R, what you can do is just declare it as a factor and it does it for you. Do you understand? So yeah. So no, it's not the same. And that's a very good question. It's something you should avoid at all costs because it throws everything out. Okay? Any other questions? Okay, thank you very much. And sorry for going 15 minutes over time.